Bismillahirrahmanirrahim. My name is Ghayasuddin, and this is our first lecture towards quantum mechanics. Our topic is the black-body radiation. We need to understand the basic idea of what is black-body radiation, because this is very important. In our next lectures, we will do a step-by-step calculations of the Rayleigh-Jeans law. We will discuss the ultraviolet catastrophe, then we will discuss the Wien's displacement law, and in the last lecture of this black body radiation, we will discuss the Max Planck's law, how he successfully explained this black body radiations. So according to classical mechanics, if this is a particle, so the characteristic of this particle is that this particle has some energy E and a momentum P. And according to classical physics, if this is a wave, so this have some wave vector k is equal to 2 pi over lambda, and this is a wave vector which describe the direction of the propagation of this wave. And this wave have also a characteristic of this amplitude A. So now, according to the classical mechanics, this wave can exchange any amount of energy with this particle, and this is the main problem, that a wave can exchange any amount of energy with the particles. So this leads to the failure of classical mechanics, which fails to explain a number of microscopic phenomena such as this black body radiation, the photoelectric effect, and the Compton effect. So we will discuss a few words for a black body radiation, that what is black body radiation, because there is a lot more for black body radiation, the Rayleigh-Jeans, Wien's displacement, Stefan-Boltzmann, and the Max Planck's law. So the main idea of the black body radiation is we can define the black body as an ideal body which absorbs all the radiation incident upon it, regardless of frequency. Such a body is called black body. So when a body which is absorbing all the electromagnetic radiation which is incident upon it, so whatever the frequency is or whatever the wavelength is, so this body we call the black body, and the radiation which is emitted from this black body, then what we call is the black body radiation. So this is an ideal body, but we can approximate this black body. Before this, if we talk about questions like how the radiation is interacting with matter. So basically we say that if this is a body and an incident radiation, this is fall on this body, so we can say that some of the radiation may be reflected, some of the radiation can be absorbed in this body, and some of the radiation may be transmitted from this body. So in room temperature, if we talk in room temperature, a body is every object is radiating electromagnetic radiation. For example, this is a person and which is sitting in his room. Okay, so it does not mean that this body, this person is not radiating. So actually it is radiating at a room temperature, and the radiation is the infrared radiation, and the infrared radiation is invisible to our eye. So I talk about that all the radiation upon it, regardless of its frequency. So we can go to the electromagnetic spectrum. For example, this is the electromagnetic spectrum in which all the radiations are present. For example, from gamma rays and to radio waves, there is more radiation like cosmic rays also is present. So this part from violet to red, from 400 nanometers to 700 nanometers, which is called the visible light, and the spectrum of this is called the visible spectrum. Our eyes is only restricted to see only this part of the electromagnetic spectrum, from violet to red, and we cannot see less than more than this and less than this for any wavelength or frequency. So this is the shorter wavelength, and this is the longer wavelength. So in this case, if we write regardless of its wavelength, this is also correct, because we know that the wavelength is equal to 1 over f, and f is equal to 1 over lambda. So if we say that the lambda is shorter, this is so the frequency will be more. So in this case, if the lambda is short, so this have higher frequencies. And if we look to this radio waves, so if the wavelength is longer, so this have a lower frequency waves. And like this, we can understand all the rays like X-rays, ultraviolet radiation, infrared radiation, and microwave radiation. This is the electromagnetic spectrum. So far, an ideal body which absorb all these radiation incident upon it, so that body will called the black body, and the emitted radiation from that black body, then we will call Blackbody radiation. So if we look to this metal, this is glowing. So now we all know about the metal which is glowing, which gives visible light. So this light we can see whose color is changed with the temperature of this metal, which is going from the red to yellow and then to white as it become hotter and hotter. So in this case, other frequencies are also emitted, which our eye cannot see these radiation. So as I said that at room temperature, most of the radiation is in the infrared part of the spectrum, which is invisible to us. So the ability of a body which absorb all the radiation is related to the ability that it will be emit that radiation too. So we can practically or experimentally approximate this black body, because it is impossible to take it in real life in real cases, but we can approximate these black body as a black hole. This is a black hole, and we can say that this black hole is a black body, and the radiation which is emitted from this is the Hawking radiation. So we can approximate a black body experimentally. We can say that, for example, we have this body, and there is a hole in this body, and if a radiation is incident on this body, so what will happen to this radiation which is incident on this body? So this will come here, then it will be reflected from here to here, so to the point multiple reflections will occur in this body to this incident radiation. This incident radiation will enter to this body, and due to multiple reflections, this radiation will get absorbed in this body. So all the radiations, regardless of its frequency or wavelength, when it is absorbed in this body, so when this is what we call the black body. So now if we give the temperature T to this object, so it will start radiating. So that radiations is called the black body radiations. So we get a spectrum for this black body when a body is heated. So we can get a spectrum like this for different temperatures, like T is equal to 4500 Kelvin, and 4000 Kelvin, 3500 Kelvin, and 3000 Kelvin. This is different temperatures. So a black body is only depends on the temperature of the body. It is not dependent on the structure of the body, on the shape of the body, or any other chemical composition of the body. So it is only depend on the temperature of the body. So we get like this spectrum when we heat the black body at a different temperature. In this case, we take the spectral emissive power with the radiation, with the wavelength. We can also take this with a frequency f, because the frequency is, I told that frequency is equal to 1 over lambda. So in this case, the wavelength is shifting towards this side, but if we take the frequency here, then it will shift towards this side. So there is a peak at every temperature, at every lambda, or at frequency, particular frequency, there will be a peak. So to explain this behavior of this spectrum, that what is going on here, so we will discuss the laws to explain this spectrum one by one, that how the Max Planck solve this this spectrum. We will talk about in our next lectures about this spectrum.